Hello and welcome to this latest demonstration of Icon Science's RokDoc software. In this video, we'll be focusing on RokDoc's Reservoir Characterization module, a powerful and interactive geophysical modeling, seismic inversion, and seismic reservoir characterization package. For the purposes of this demonstration, we'll be focusing on the appraisal of a discovered oil field. We have multiple appraisal wells, offset exploration wells, and seismic reflection data with interpretation covering the field. The aim is to use the seismic data to better understand reservoir geometry and architecture, and ultimately to predict reservoir properties from seismic. The analyses performed here are based on a robust rock physics analysis of the well data. This type of work is best done in RokDoc's industry-leading rock physics module. Please see the accompanying video for more details on this module. This is the RokDoc project view. Here we see the locations of the well and seismic data. Amplitudes extracted from the seismic data are shown, and it can be seen that a wide range of responses are observed in the seismic across the field. Reservoir characterization sessions are based on a seismic survey geometry and can be defined in either depth or time. Well, horizon, and volume data can be added to the session. The volume data can be individual volumes or Prestack data such as angle or offset gathers. The session can be viewed along any selected inline, crossline, or arbitrary line, and multiple views can be displayed simultaneously. All data items are selected from the data tree. The horizons selected in the session setup are used to define zones. Data can be displayed by selecting it from the tree. All processes performed in the session are initially generated as interactive recipes that can be calculated on the displayed sections. Recipes can be linked together with the results generated on the fly. The zonation and stratigraphy can be controlled by the user. For example, horizons can be specified as being conformable or as unconformable. A depth conversion can also be specified and can be generated based on a number of methods. Once this has been set up, a session depth conversion recipe is generated. This allows the velocity field to be displayed. Here the velocity field is co-rendered with the seismic data. Once a depth conversion has been generated, all data in the session can be viewed in either depth or time, regardless of the native domain. An option to flatten on a particular horizon is also provided. Here the data is shown relative to the top reservoir pick. The model framework can be populated with geological and elastic properties within the base property model. The properties within this model can be defined based on a number of different methods. These include interpolation, rock physics models, depth trends, seismic inversion data, and data from geogrids and flow simulators. The model is populated on a zone-by-zone basis, and within each zone and for each property, a number of methods are available. Depending on the method selected, there are a number of techniques provided. For example, in the case of interpolation, various kriging options are provided. A variogram analysis tool is also included. In this example, some zones have been populated with elastic data from seismic inversion, and others with rock physics models. When predicting elastic properties from geological properties using rock physics, access to the rock physics model variables is provided. Here, geological properties have been loaded from a corner point grid, and the selected rock physics models predict elastic properties based on this information. The properties within the base property model are interactive recipes and are calculated on the fly. Here the porosity from the corner point grid is displayed. The P-wave velocity is formed of different methods in different zones. Within the reservoir zone, the velocity is calculated from the grid properties using the selected calibrated rock physics model, with a variety of other methods used in other zones, including depth trends, well interpolation, and elastic properties from seismic. The properties in the base model can be compared to well data and rock physics models in the crossplot. Here we see porosity versus P-wave velocity for both the well data and the base property model, calculated along the displayed line. Rock physics models are overlain. We can also review the log and model data in different spaces. For example, here P-wave velocity versus S-wave velocity is shown. The rock physics model automatically transforms to the selected variables. 3D fluid substitution can also be performed within the module. Here the in situ saturation is described by SW from a corner point grid. A recipe can be defined using Gassman's equation to perform fluid substitution to any saturation of interest. The recipe is based on the geological and elastic properties within the base property model. The fluid substitution is performed on a zone-by-zone basis and can be defined within multiple zones. The dry rock response for the sandstones along the displayed line are shown. This is normalized dry rock bulk modulus versus porosity crossplot. A dry rock model can be imposed here if required. Any fluid saturation in the reservoir can be modelled and fluid contact imposed. Here, 100% brine saturation is modelled. Once this is done, a new recipe is saved, which allows the fluid substitution to be run on any displayed line. The difference in velocity between the in situ saturation and the 100% brine saturation is shown here. Residuals, or the difference between the two properties, can also be calculated as a recipe. Here we see the difference in velocity between the in situ saturation and the brine saturation as predicted by the rock physics models. Any synthetic impedance or reflection attribute can be generated from the property models. Either the base or any perturbations made, such as the fluid substitution just performed. We will generate a synthetic full stack here, but pre-stack synthetics or any impedance attribute can also be constructed. An angle range for the synthetic attribute can be specified here. A 1D convolution technique is applied, and a wavelet can be selected from the database. For more information on quantitative wavelet estimation, please see the accompanying video. Various reflectivity equations are provided, including 2- and 3-term equations. Once the recipe has been calculated, it is displayed along the line. Here, the synthetic attribute is shown as a wiggle overlaying on the p-wave velocity property model. Any trace data, seismic or synthetic, can be displayed as a color variable or as wiggles. A visual comparison is made here between the synthetic and the seismic, and a residual recipe could also be defined. Other tools for comparing synthetic to seismic data are provided by the Reservoir Characterization module. Any pre-stacked synthetic or seismic data included in the session can be displayed at each trace location, either as individual angles or offsets from the gather, or as all offsets or angles at each CDP, with all angles shown at each trace location. Zooming in allows us to see the pre-stacked data more clearly. Attributes can be extracted from any volume or recipe within the session. As an example, we will extract the AVO at the top reservoir pick from the pre-stacked seismic data. A range of attributes can be extracted from both single volume and pre-stacked data. The extraction parameters are selected here. The attribute is calculated along the displayed line and shown in the lower attribute plot. The line thickness and color can be selected by the user. The attribute plot now shows the AVO at the top reservoir pick, which can be compared to the data in the section. A wide variety of attributes can be extracted from any volume or recipe. This includes thicknesses, averages, or correlations, such as cross-correlation or PEP. Seismic inversion data can also be included in the session. The acoustic impedance from a seismic inversion is shown along the line. Log data can also be plotted at all well locations, and logs can be shown at the wells automatically. Here the upscaled acoustic impedance log curve is plotted. A log search tool is provided that allows the rapid selection of log data for display. Once displayed, a comparison between the inversion data and log data along the section can be made. The Reservoir Characterization module includes a number of seismic inversion methods. These include traditional model-based inversions, as well as Icon Science's award-winning joint impedance and facies inversion technology. In addition, advanced seismic data conditioning tools are available to ensure that the seismic data is optimized for amplitude work. Please see the accompanying video for more information on these add-ons. For the purposes of this example, a demonstration of how geological information can be extracted from impedances will be shown. This is the aim of seismic reservoir characterization. We look to determine rock types and geological properties from seismic data. A number of tools are provided to perform this analysis. These include a polygon indicator technique, where a discrete classification of continuous impedance data is made based on cross-plot polygons, a Bayesian classification technique, where impedances are classified based on a prior model, and the use of rock physics models to predict geological properties from impedance data. We will begin by reviewing the cross-plot polygon method. Cross-plot can be used to plot well data, volume data, and data generated from recipes within the session. The aim here is to define polygons in the relevant impedance space based on the responses observed at the wells. Here we are basing the classification on acoustic impedance versus VP over VS ratio, but any combination of elastic attributes could be used for this process. An interactive approach is taken where the data is highlighted within the session view. If the polygon is adjusted, the classification in the view updates automatically. Another useful tool within the Reservoir Characterization module is the map viewer. Maps can be generated as slices through the data, either constant time or depth, or from any defined attribute. Here an extraction through the polygon classification is made so that the lateral distribution of the oil-saturated sands can be reviewed. This is the first step towards extracting meaningful geological information from the seismic and seismic inversion data. Next, a more sophisticated technique will be used to generate a discrete facies volume from inverted impedances. This is a Bayesian classification of the inverted impedance data based on a prior model. The prior model represents our understanding of the elastic properties of each facies, including the spread of the impedance responses within each facies. In this case, the prior model will be generated from well data using the crossplot. Again, the prior model is defined in AI VPVS ratio space, but any combination of elastic attributes could be used. Here the prior model for 3 facies that are defined based on Gaussian ellipses are shown. A 3D view is also provided for QC, and the PDFs can be edited and the prior probability specified here. Once the prior model has been defined, it can be used to make a classification of the impedance data. Here the facies classification is shown along the viewed line. The inversion data at each sample along this line has been classified based on the prior model. We can show the facies classification made at the wells based on the log response for comparison to that made from the seismic response, and this again can be done within a few button clicks. We can also use the map viewer to track the lateral distribution of the facies classification. An horizon following slice through the top of the reservoir will be extracted from the facies cube. In this case, we have classified a number of different facies that can be tracked across the volume. The hydrocarbon-bearing sands are shown in green, the brine-bearing sands are shown in yellow, and the intra-reservoir shale is shown in grey. Furthermore, we can use attribute extractions to calculate a two-way time thickness of the hydrocarbon-bearing sands based on the facies classification, and this is shown here. Facies classification is the most likely from the Bayesian technique. We can also review the posterior probability from the Bayesian classification technique. One set of posterior probabilities is produced for each facies classified. This gives us insight into the robustness of the classification across the volume. The final step that I will show in this demonstration is the use of rock physics models to predict geological properties from seismically derived impedances. This is done by using a calibrated rock physics model in a reverse sense as a lookup table. The rock physics model is the link between the geological properties we're interested in and the elastic impedance responses we estimate from seismic. Here, a model has been calibrated at the wells with a mesh that shows lines of constant volume of shale. One mesh is for brine-saturated rocks and one is for oil-saturated rocks. The model is plotted in AI VP over VS ratio space, but any combination of elastic properties can be used. The rock physics model can be used to generate properties from the inverted seismic data. Here, porosity is shown that has been calculated from the inverted impedances using a rock physics model. The rock physics model is applied per facies using the facies classification of the impedance data performed previously. This is important, as the appropriate rock physics model will change per facies, and we need to understand how the facies are laterally distributed across the volume in order to correctly apply the rock physics models. Again, we can use the map view and attributes to understand how the porosities and other geological properties vary across the area of interest. Finally, a 3D viewer is also provided. This allows the display of any data item in the session in 3D. This includes all well data, any interactive recipes, and 3D volume data. We can scroll through any 3D data item. For example, here the full stack seismic response is shown along an inline. The well data is also plotted with the well log based facies classification displayed. Any volume data can also be rendered in 3D. Here the facies classification is shown. This is a powerful illustration of how the workflows performed within this demonstration are able to extract meaningful geological information from the seismic data. We now have an enhanced understanding of not only the geometry and layering of facies, but the geological properties within those facies. For more information, please contact info@iconscience.com or visit our website at www.iconscience.com. Thank you for listening.